We're talking about when a function is increasing and when it's decreasing, on what intervals that's happening. If we go back to the example we started out this section with, this is a function that would be increasing on the interval from -6 to 2, decreasing on the interval from 2 to 8, and then increasing on the interval from 8 to 11. Notice those are all intervals, like sections of the x-axis. And they follow one another. You go from -6 to 2, then you start at 2 and go to 8, then you start at 8 and go to 11. There's no overlap because you can't be increasing and decreasing at the same time. So what about this function? Where is it increasing and where is it decreasing? Well, look at the graph. It's only defined from -2 to 2. So we're going to take that interval from -2 to 2 and divide it up into maybe the part of that where the function is increasing and the part where it's decreasing. So if you trace along the graph from left to right, pay attention to where you're headed upward and where you're headed downward. So the part where we're headed upward is the part where x is between -2 and 0. And the part where we're headed downward is where x is between 0 and 2. So we can say this function is increasing on the interval from -2 to 0, and it's decreasing on the interval from 0 to +2. Now here I wrote these as open intervals, but if you wanted to include the endpoints, you could. So I'm not going to be picky about whether you write these as open or closed intervals with the square brackets or the round parentheses. What about this function? Again, as you trace along from left to right, during this part of the graph, we're headed upward. Then we're headed downward. And then we go back up again. So what are the intervals where that happens? We are increasing on the interval from -infinity to -1, and on the interval from +1 to +infinity. And we are decreasing on the interval from -1 to 1. How about this one? What happens here as we go along from left to right? Well, let's see. At first, we're headed downward. And then we have this big gap. The graph is kind of in two separate pieces because it's undefined at 0. But we looked at the parts over here where x was less than 0 and the function was decreasing over here. Now look at the part over here where x is greater than 0. It's decreasing over here as well. So this function is decreasing on the interval from -infinity to 0 and also on the interval from 0 to infinity. Now here I definitely should use the round parentheses. I don't want to include 0 because the function's undefined at 0. That's not even part of the domain. Okay, now what about this one? One hint I've heard is that if you're looking for where a function is increasing or decreasing, it can help you avoid getting distracted if you cross out the numbers on the y-axis. We don't care about the y-coordinates. We don't care that we go from a point where y is -1 up to a point where y is 3. When we talk about the intervals where a function is increasing or decreasing, we're talking about the range of x's, the part of the domain of the function, the x-axis. So here we are decreasing on the interval from -infinity to -1, and then -1 is where we change over, and then we're increasing from -1 to 1 on that interval, and then we're decreasing again on the interval from 1 to infinity. Now notice at the places where we change over from increasing to decreasing or decreasing to increasing, those are turning points. They might be a high point, they might be a low point. And we call those, well, a high point is a relative maximum. And if you have more than one of them, the plural is maxima. And a low point is a relative minimum. And if you have more than one of those, the plural is minima. So a relative minimum is the lowest point on that part of the graph. It's where the function has a value at that point that's lower than it is at any other nearby point. So it might not be the lowest point on the entire graph, but it's the lowest point on that part of the graph. If you're at a relative minimum, you're not going to be able to get any lower, at least without leaving that neighborhood of the graph. And a relative maximum is like a mountaintop. It's maybe not the highest mountaintop, but it's the highest point on that particular hill. So if you're at a relative maximum, you can't get any higher unless maybe you go down off that hill and go climb a different hill. So what about this graph? Can you see where there is a relative maximum or a relative minimum? Yeah, there's a relative maximum here at -1, 4. The point where x is -1 and y is 4. And there's a relative minimum at this point here where x is 1 and y is 0. Now let me just mention that here we're focusing on graphs and how you can see all this increasing, decreasing, relative maximum, relative minimum from looking at a graph. Now if you ever go on to take calculus, one of the big things you spend a lot of time studying in calculus is how you can figure out just from the function itself, just from the way it's defined, that equation, and doing calculus kinds of things to that, how you can figure out where a function is increasing, where it's decreasing, where it has a relative maximum, where it has a relative minimum. So by using calculus techniques, you can pinpoint exactly where all of those things happen, even if you didn't have a graph to look at. And for our last example, going back to this one, see it's got a high point here. That would be, that would be the relative maximum there at the point 0, 4. Now there it happens to be the absolute maximum, the highest point anywhere on the graph, but it also counts as a relative maximum. And if you're wondering whether these points here at -2, 0 and +2, 0, are those relative minima? Well, it kind of depends on exactly how you define what a relative minimum is, but the problem is that's kind of where we stop. We can't keep on going because it's not defined past there. So if a relative minimum is a point that's lower than all the other nearby points in that neighborhood, well, there are some points in the neighborhood where the function's undefined. So that makes it a little tricky. Do we call this a minimum point or not, a relative minimum? So we're just not going to worry about that.